Welcome, cosmic explorers, to a journey into the most mysterious and mind-bending corners of the universe. Today, we're diving deep into the enigma of black holes, the universe's most captivating phenomena. These invisible giants twist space, warp time, and challenge everything we think we know about reality. What are black holes? How do they form? What happens if you fall into one? And why do they hold the key to unlocking the secrets of the cosmos? Buckle up, because we're about to embark on an epic adventure that will stretch your imagination and leave you hungry for more. Let's unravel the mystery of black holes together. First, let's paint a picture. Imagine a region of space so dense, so packed with mass, that nothing, not even light, can escape its grip. That's a black hole in its simplest form. It's not a solid object like a planet or a star, but a gravitational powerhouse, a place where the laws of physics are pushed to their limits. The idea of black holes sounds like science fiction, but they're very real, and they've fascinated scientists, astronomers, and dreamers for centuries. From their theoretical roots to the stunning evidence we've uncovered, black holes are a testament to the universe's wild creativity. So, where did this bizarre concept come from, and how do we know they exist? Stick with me, and we'll find out. The story of black holes begins with a genius and a revolutionary theory. In 1915, Albert Einstein published his theory of general relativity, a game-changer in how we understand gravity. Instead of a force pulling objects together, Einstein described gravity as a curvature of space and time, like a bowling ball sinking into a stretched rubber sheet. Massive objects warp the fabric of spacetime, and the more massive the object, the deeper the dent. Now, take that idea to the extreme. What happens if you cram an enormous amount of mass into a tiny space? The curvature becomes so intense that it creates a bottomless well, a region where gravity is so strong that escape is impossible. This was the seed of the black hole idea, first hinted at in the 18th century by thinkers like Jean-Michel and Pierre-Simon Laplace, who wondered about dark stars, too massive for light to flee. But Einstein's equations gave us the tools to truly explore this cosmic puzzle. Let's meet the architect of modern black hole theory, Karl Schwarzschild. In 1916, just months after Einstein's breakthrough, this German physicist found a solution to the equations of general relativity. He described a theoretical object with a boundary called the event horizon, a point of no return. Anything crossing this invisible line, whether matter, light, or even information, gets trapped, vanishing from our view. The radius of this boundary, now called the Schwarzschild radius, depends on the object's mass. For example, if you squeeze the Sun down to a sphere about 3 kilometers across, it would become a black hole. For Earth, the radius is a mere 9 millimeters, smaller than a marble. These early ideas were purely mathematical, but they set the stage for a cosmic revolution. Doesn't that make you wonder what kind of power could collapse a star into such a tiny, unstoppable force? So, how do black holes form in the real universe? The most common type, called stellar mass black holes, are born from the dramatic deaths of massive stars. Stars are cosmic furnaces, fusing hydrogen into helium for millions or billions of years, balancing gravity's inward pull with the outward push of energy from fusion. But for stars at least 8 times the mass of our Sun, the end is spectacular. When the star's fuel runs out, gravity wins. The core collapses in a fraction of a second, shrinking to an incredibly dense point. The outer layers explode outward in a supernova, one of the universe's most brilliant fireworks, while the core, if massive enough, becomes a black hole. The collapse is so extreme that the star's mass, sometimes 10, 20, or 30 times the Sun's, squeezes into a point with no volume, a singularity, where density and gravity become infinite. It's a mind-boggling concept, and we'll dive into singularities soon. But for now, picture a star's grand finale giving birth to a cosmic enigma. Not all black holes are stellar leftovers, though. At the hearts of most galaxies, including our Milky Way, lurk supermassive black holes, monsters with masses millions or even billions of times that of the Sun. The one in our galaxy, called Sagittarius A star, weighs in at about 4.3 million solar masses, packed into a region roughly the size of the Sun's orbit around Mercury. How do these giants form? Scientists think they start as smaller black holes, perhaps from early stars, and grow by gobbling up gas, dust, and other black holes over billions of years. Some may have formed in the chaotic early universe, when dense pockets of matter collapsed rapidly. Others might grow through galaxy mergers, combining smaller black holes into colossal ones. These titans shape entire galaxies, influencing star formation and cosmic evolution. Isn't it wild to think a single object could hold such sway over the cosmos? Let's zoom in on the anatomy of a black hole. At its core lies the singularity, a point of infinite density where our understanding of physics breaks down. Surrounding it is the event horizon, that fateful boundary we mentioned earlier. Cross it, and there's no turning back, gravity's pull is absolute. But just outside, things get weird and fascinating. Matter falling toward a black hole forms an accretion disk, a swirling ring of gas and dust heated to millions of degrees by friction and gravity. These disks glow brightly, emitting X-rays and other light we can detect with telescopes. Some black holes also shoot out jets, streams of particles accelerated to nearly the speed of light, blasting across space for thousands of light years. These features, accretion disks and jets, give us clues to spot black holes, since we can't see them directly. The dance of matter around these invisible giants is like a cosmic spotlight, revealing their presence. Now, you might be asking, how do we know black holes are real if they're invisible? The evidence is compelling and comes from multiple angles. First, astronomers watch stars and gas move near suspected black holes. In the Milky Way, stars orbit Sagittarius A star at incredible speeds, whipped around by a massive, unseen gravity source. The math points to a black hole. Then there's the light show from accretion disks. X-ray telescopes like Chandra and XM Newton detect intense radiation from superheated matter spiraling into black holes. But the crowning achievement came in 2019, when the Event Horizon Telescope, a global network of observatories, captured the first image of a black hole in the galaxy M87. It showed a dark shadow, the event horizon, surrounded by a glowing ring of light, exactly as theory predicted. That image, my friends, was a triumph, proof of black holes' existence. Doesn't that make you eager to learn what else we've discovered? Let's talk about time and space near a black hole, because this is where things get truly bizarre. Einstein's general relativity tells us that gravity warps not just space, but time itself. Near a black hole, time slows down dramatically, a phenomenon called gravitational time dilation. Imagine an astronaut approaching the event horizon. To an observer far away, the astronaut's clock would tick slower and slower, almost freezing as they near the boundary. For the astronaut, time feels normal, but if they could return, they'd find centuries or millennia had passed for the rest of us. This isn't science fiction, it's science fact, rooted in Einstein's equations. Space gets warped too, stretched and twisted like a cosmic funhouse mirror. Close to a black hole, the fabric of spacetime bends so sharply that paths loop inward, trapping everything. Doesn't that twist your sense of reality? What happens if you fall into a black hole? It's a question that sparks endless curiosity. Let's imagine you're a brave explorer drifting toward one. As you approach the event horizon, gravity intensifies, but for a supermassive black hole, you might cross it without noticing, at first. The event horizon isn't a physical wall, it's just the point where escape becomes impossible. But as you fall closer to the singularity, gravity's pull varies wildly. Your feet, closer to the center, feel a stronger tug than your head, stretching you like a cosmic noodle in a process called spaghettification. For a stellar mass black hole, this tidal force rips you apart before you even reach the event horizon. For a supermassive one, you might survive longer, but the singularity awaits, a point of infinite density where physics as we know it collapses. What happens there? We don't know, and that mystery fuels our quest to understand the universe. Now, let's explore a wild idea from the brilliant physicist Stephen Hawking. In the 1970s, he proposed that black holes aren't completely black. Combining quantum mechanics and relativity, he suggested black holes emit a faint glow, now called Hawking radiation. Here's how it works. Quantum theory says empty space isn't truly empty. Pairs of virtual particles and antiparticles constantly pop in and out of existence. Near a black hole, one might fall in while the other escapes. If the one that falls in reduces the black hole's mass, the escaping particle carries energy away, making it look like the black hole radiates. Over vast timescales, this process could shrink a black hole until it evaporates completely. This idea bridges two pillars of physics, relativity and quantum mechanics, and hints at deeper truths. Isn't it fascinating to think black holes might slowly vanish, leaving whispers of radiation behind? Let's dive into the types of black holes, because they come in a surprising variety. Stellar mass black holes, born from dying stars, range from a few to tens of solar masses. Supermassive black holes, like the ones in galaxy centers, dwarf them, weighing millions or billions of solar masses. But there are others. Primordial black holes, a theoretical type, might have formed in the dense, chaotic early universe, with masses as small as a mountain or even less. If they exist, they could explain some of dark matter, the mysterious substance shaping the cosmos. Then there are intermediate mass black holes, bridging the gap at hundreds to thousands of solar masses, possibly forming from star clusters or early mergers. Each type raises questions. Could tiny black holes still lurk out there? How do supermassive ones grow so fast? The variety keeps us guessing. Black holes also play a starring role in the universe's grand drama. Supermassive black holes at galaxy centers influence their surroundings profoundly. Their gravity pulls in gas and dust, fueling star formation, while jets from accretion disks blast energy across space, heating gas and shaping galaxy evolution. Some scientists think black holes and galaxies co-evolve, growing together over billions of years. Black holes also merge, creating even bigger ones. When two black holes spiral toward each other, they warp spacetime, sending out ripples called gravitational waves. In 2015, the LIGO Observatory detected these waves for the first time, from two stellar mass black holes colliding 1.3 billion years ago. That discovery, another Nobel Prize winner, confirmed Einstein's predictions and opened a new way to study the universe. How cool is it that we can hear black holes dancing across the cosmos? Let's tackle some mysteries and paradoxes. One big puzzle is the information paradox. Quantum mechanics says information, like the properties of particles, can't be destroyed. But if matter falls into a black hole, past the event horizon, does that information vanish? Hawking's radiation complicates things. If black holes evaporate, where does the information go? Some physicists propose it's encoded in the radiation, others suggest it's stored on the event horizon, like a cosmic hologram. Another mystery, what's inside a black hole? The singularity defies our physics, hinting at a need for a theory of quantum gravity, blending relativity and quantum mechanics. Ideas like string theory or loop quantum gravity try to bridge this gap, but we're still searching. These puzzles make black holes a frontier of discovery. Don't you want to know the answers? Let's look at how we study black holes today. Telescopes like the Event Horizon Telescope capture images by linking observatories worldwide, creating a virtual dish the size of Earth. X-ray observatories detect the glow of accretion disks, while gravitational wave detectors like LIGO and Virgo listen for cosmic collisions. The James Webb Space Telescope, launched in 2021, peers back to the early universe, hunting for clues about how supermassive black holes formed. Computer simulations model their growth and behavior, testing theories against observations. Every tool brings us closer, yet black holes keep some secrets just out of reach. Future missions, like the LISA Space Observatory, will hunt gravitational waves from supermassive black hole mergers, promising new insights. The hunt is on, and it's thrilling. Now, let's address some myths. Black holes aren't cosmic vacuum cleaners, sucking up everything. If our sun turned into a black hole, Earth wouldn't get swallowed, we'd orbit as usual, just colder. Their gravity only dominates close to the event horizon. Another misconception, black holes are rare. They're not. Billions likely exist, from stellar remnants to galactic giants. And no, they don't destroy the universe, they're a natural part of its cycle, shaping galaxies and recycling matter. Some even wonder if black holes could be portals to other universes, a staple of sci-fi, but there's no evidence for wormholes yet. These ideas spark imagination, but the real science is just as exciting. What does all this mean for us? Black holes challenge our understanding of space, time, and physics. They're laboratories for testing relativity, quantum mechanics, and the nature of reality. They connect us to the universe's story, from the deaths of stars to the birth of galaxies. The atoms in your body, forged in ancient stars, tie you to the cosmic dance of creation and destruction, where black holes play a starring role. They remind us how small we are, yet how vast our curiosity can be. Humans have gazed at the sky for millennia, wondering about our place, and black holes push us to keep asking, keep exploring. As we near the end of our journey, let's gaze forward. Black holes remain enigmatic, but each discovery peels back a layer. Future telescopes and detectors will map more black holes, probe their interiors, and test theories of quantum gravity. Could they unlock the universe's deepest secrets? Might they reveal new physics, or even hints of other dimensions? The questions are endless, and that's the magic of black holes. They're not just objects, they're gateways to wonder, challenging us to rethink everything. What mysteries do you think they'll unveil next? How far will our quest take us? Thank you for joining me on this epic dive into black holes, the universe's most enigmatic phenomena. I hope your mind is buzzing with curiosity. If you love this cosmic adventure, hit that like button, subscribe, and ring the bell for more journeys into the unknown. Drop your thoughts in the comments. What blows your mind about black holes? What cosmic mystery should we explore next? Until then, keep looking up, keep wondering, and let's unravel the universe together. See you in the next video, Cosmic Explorers.